In this video, we're going to look at projectile motion in the Earth's gravitational field. All right, so we're going to imagine a particle being launched from the ground. It's going to be subject to acceleration in the Earth's gravitational field, and we're going to just analyze that motion and build up a general expression for any kind of projectile motion. All we really need to know is the initial speed with which the particle is launched and its angle. Okay, what speed is it launched with and its angle to the ground, and then we can analyze any kind of projectile motion. Okay, so very important with these sort of problems is we should choose a direction before we start. So what I'm going to do is I'm going to choose up as plus and to the right as plus, because it matches my diagram. Motion to the right I'll take as positive, motion upwards I'll take as positive. So anything falling down then will have a negative. Okay, anything moving in the Earth's gravitational field will be subject to acceleration down towards the center of the Earth, and so the acceleration will be in a negative direction. Okay, just bear in mind that. That's the only other thing to consider. And so here we go. Let's have a look at a projectile launched at some angle to the ground with some initial speed v0. Okay, now we can analyze this as a two-dimensional problem because the direction into and out of the plane is not relevant here. We're only interested in motion to the right and motion up or down. Okay, as the projectile rises, as the projectile falls. So it's really a two-dimensional problem because this projectile motion tends to be in a straight line. You tend to launch an object, it tends to be in a straight line. Okay, I mean, air resistance can pull it off, and you kick a football and it experiences air resistance as it tumbles and so on, and that can change its direction. And if there's a wind there, that can push it and all the rest of it. Okay, but let's imagine if we were in a vacuum and we launched in a particular direction, it will just travel in that straight line. However, when I say a straight line, I'm excluding the fact that it's going to rise and then it's fall, but I mean its direction to the right there, from left to right, is going to be in a straight line. Okay, so let's start with something here. We know that it's given an initial speed v0. It has, if we were to write this as a vector, turn this into a velocity vector because it's given an initial velocity, okay, upwards and to the right. It has a component in the horizontal direction, it has a component in the vertical direction, and this component in the horizontal direction will be v0 times cos theta. Okay, it's really just a right angle triangle here. Okay, there's your vector. Okay, v0, here's some angle theta. Then what we have here, this side here, okay, will be opposite sine theta. Okay, will be sine theta will be opposite on v0, and so the magnitude of this side, okay, will be v0 sine theta. Now, okay, so the y component of the velocity, I probably could have helped myself by just calling it the y component instead of mucking around. Okay, let me change all that then. No, I don't like that. Okay, let me call this Vy, and so that's Vy, and that's Vy. Okay, same with cos, it's going to be, this will be Vx, and so we're going to have cos theta will be Vx on V0, and so Vx is just going to be V0 cos theta. Okay, now the other thing to consider, so our initial velocity vector at t equals 0 then, we'll have v of 0 will be v0 cos theta, that's the velocity in the horizontal direction, plus v0 sine theta, that's the velocity in the vertical direction, so vx and vy. Okay, one other thing to consider, any object moving in the Earth's gravitational field will be subject to an acceleration towards the center of the Earth. That acceleration will be equal to g So A will be minus G because it's going downwards, so we must give the negative a value. And it's going downwards in the J direction. So the acceleration at all times, sorry, not just initially, but the acceleration at all times is this object here, minus G meters per second if it's in those units, in the J direction, in the negative J direction. So minus G times J component. Okay, so our velocity vector in general for this projectile motion, take into account those two facts, okay, will be the integral of the acceleration vector, okay, that's this one, with respect to time, plus a constant vector. We'll call that constant C1 because there'll be another constant when we go looking for the position vector. So that's minus G dt in the J direction, the integral of minus G with respect to t in the J direction plus C1. Well, carrying out that integration, we get minus G times t in the J direction plus C1. Okay, so that tells us that V of t is minus G times t in the J direction plus C1, and all that remains now is to find C1. Now we do have that information because initially it was projected at some angle with respect to the Earth, okay, some angle theta. It was projected with an initial speed v0 in a given direction from which we constructed the velocity vector. Remember, a vector has speed and direction. So at t equals 0, we have v of 0 is v0 times cos theta, as we worked out over here, plus v0, whatever it is, times sine theta in the J direction. Okay, I'll put plus there because upwards is positive and to the right is positive. Okay, so that keeps everything here positive and keeps the vector quite simple. Okay, whatever v0 is, v0 is the initial speed with which it's launched, and that depends on how much energy the projectile is given. Okay, what's the initial velocity it's given? Okay, so v at 0 is equal to c1 is this object here. Okay, so what we're saying is that at t equals 0, minus g times t is 0 in the, okay, so that drops out, and v of 0 is just c1, so v of 0 equals c1, so c1 is simply this object here now. And what that means then is that our velocity vector in general, so the velocity of the projectile any time t now, is minus gt in the J direction plus v0 times cos theta in the I direction plus v0 times sine theta in the J direction. Well, there's two J components here, so we combine them. So finally, our velocity vector at any given time t, from t equals 0 onwards, is going to be v0 times cos theta in the I direction plus v0 times sine theta minus gt all in the J direction. That's the velocity of the particle at any time t. Now at t equals 0, we have the projectile at t equals 0, the instant it was launched, its position vector is the origin 0. Okay? It's just at the process being launched, so it's on the ground here, it's about to be launched. At t equals 0 is the instant it's still touching the ground. Okay? Well, to find the position vector, we need to anti-differentiate the velocity vector and add a second constant vector. Okay, plus some constant vector. So that's the integral of v0 cos theta in the I direction, integrated with respect to time, plus the integral of v0 sine theta minus gt in the J direction, integrated with respect to time, plus our constant vector. Okay, well, anti-differentiate this, well, there's no functions, explicit functions of t there, so that simply becomes v0, the initial speed, times time, times cos theta in the I direction. For this business here, same thing, v0 times t times sine theta. Notice there's no explicit dependence in the cos or sine terms on t, okay? And v0 is just a constant, just a number, okay? A scalar. Okay, minus g t squared on 2 in the J direction plus some constant vector. All right, at t equals 0 though, well, all of that disappears because there's a t in every term there. So put 0 in there, all that disappears, and so C2 must be equal to 0. We were told too that the position vector at t equals 0 is also 0, so C2 must be 0, okay? Okay, well that tells us that the position vector of this projectile at any time t, or any projectile launched with initial speed v0, is just going to be v0 times t times cos theta in the I direction plus v0 times t times sine theta minus g times t squared on 2 in the J direction. And that's the position of the particle at time t. Now, okay, so this is the general expression for the position function of a particle at any time subject to projectile motion with some initial speed v0 at an angle theta, okay, with respect to the Earth, and in the Earth's gravitational field. This is its velocity vector at any time t, okay, in the Earth's gravitational field with an acceleration of g. On different planets or different bodies with different gravitational accelerations due to gravity g, you just substitute for that g there. So you could be talking about any body. Wherever you have a body that generates a gravitational field, you're going to be able to use the velocity vector here, position vector here. They cover all cases. You just have to change the value of g for whatever the acceleration due to gravity is on that body. Okay. So we have the position vector and velocity vectors at any time t. Now we know that the position vector is given by x of ti plus y of tj, and these are the Cartesian coordinates x and y. So we can find the Cartesian path of the projectile using its parametric equations. Now the parametric equations are the equations that we've parameterized in terms of the parameter t. Okay, these are the parametric equations, x of t, y of t. Okay, so x of t is v0 times t times cos theta, y of t is v0 times t times sine theta minus g times t squared on 2. Okay, well, from the first one, we can write t is equal to x on v0 cos theta. And then we can substitute that into the y of t here. Wherever we see a t, we can put this x on v0 cos theta. Okay, when we do that, we get this expression here, v0 times x on v0 cos theta times sine theta minus g on 2 times x on v0 cos theta squared. Okay, well, when we do that, sine theta on cos theta will give us tan theta. v0 on v0 will cancel out, and we'll just be left with x times tan theta. Sine theta divided by cos theta is tan theta. Here, we're going to get minus g x squared on 2 v0 squared cos squared theta. Okay, and tidying that up, we have hence y of x, the y coordinate as a function of the x coordinate is x tan theta minus gx squared on 2 v0 squared cos squared theta. Okay, now the range is found. How far does a projectile go? So it's firing away, and okay, you launch it along the ground there, launch it here, and eventually it comes down. So what's this distance along here? Okay, well, if you think about it, this point here occurs, this is y equals 0. All along the x-axis here is y equals 0. Okay, so the range is found by solving for x when y equals 0. So set y equals to 0 on the left-hand bit, so our x tan theta minus gx squared on 2 v0 squared cos squared theta is 0. Okay, well, take this second term to the right, we get x tan theta as this object here. Okay, next thing, let's cancel out an x on both sides, so we have tan theta is equal to gx on 2 v0 squared cos squared theta. Okay, and then what we're going to do is we're going to rearrange this, okay, to get x by itself. So we're going to multiply tan theta by 2 v0 squared cos squared theta and divide by g. Okay, and then this tan theta, did it all in one step here, hope it's all right by everybody, but rewrite tan theta as sine theta on cos theta. Okay, and when we do that, we get that x, the range. What is the x value here? Okay, what is it? Well, that's the range, how far it goes, because it starts x equals 0 here and ends up at some x value, and that x value occurs when y is 0. So we get x is this object here, which now can simplify because a cos squared there and a cos here, they can cancel out. And we're then left with, and I certainly wish I'd left myself more room to do that, but if I come down to the page down here, what I'm going to be left with is x is equal to 2 v0 squared cos theta sine theta, okay, and all that's over g. Now, that 2 cos theta sine theta is just equal to, well, v0 squared on g times sine of 2 theta. Remember that identity? 2 sine theta cos theta is equal to sine 2 theta. Okay, and so we end up with the range being x equals v0 squared, the initial speed squared over g, gravitational acceleration due to gravity on the body you're dealing with, in the Earth's case, approximately 9.82. Okay, and then we're going to have here sine 2 theta. Okay, and that will give us the value of x. Now, by a similar token, at its maximum height, its vertical component of velocity is 0. Okay, so at its maximum height, its vertical component of velocity is 0. And so what that means is, if we find the velocity component, here it is. Here's the y component of the velocity. So that's v0 sine theta minus gt. So that component is v0 sine theta minus gt. Now at that point, at its maximum point, there's an instant in time where the upward velocity is 0, and then it begins to fall again, just an instant in time, which means that component of the velocity vector must be 0. So v0 sine theta minus gt is 0. Solving for t gives us v0 sine theta on g, okay? And that's the time taken to reach its maximum height. So it'll reach its maximum height when at t equals v0, the initial speed, times the sine of the angle over g. And we're working, make sure if your calculator's in radian mode, that's fine. If your calculator's in degree mode, okay, make sure you've got the right units for your problem. Okay, that's it really. Job done.